Hello children, welcome to the maths classes. Today we will continue with the unit circles and we will do some sort of questions related to circles where we found the relationship between the angles drawn at the center and on the remaining part of the circle. We have this type of question where angle PQR is given 100 degrees and we have to find the measure of angle OPR. Now, how can we solve that question? First of all, we see that angle PQR is the angle that is drawn on the remaining part of the circle. We see that it is drawn on the circumference. That means this angle is the angle made on the remaining part of the circle. And another thing we learned before in previous classes, that if an arc subtends two angles, one at the center and another on the remaining part of the circle, both the angles lie on the alternate arcs of the circle. That is, if angle PQR, we observe that angle PQR is drawn in this minor arc PQR and its central angle will lie in the other arc. Every time when we draw two angles, central angle may lie in one arc and the remaining part of the circle's angle lies in the other arc. So, if angle 100 PQR lies in arc PQR, then its central angle lies in another arc, that is this PR. So, the center angle for that is reflex angle POR. So, we can say that this is the major segment PR. It subtends reflex angle POR at center and angle PQR on the remaining part of the circle. So, when we solve this question, we write that major arc PR subtends reflex angle POR at center and angle PQR on remaining part of the circle. So, it is very easy to identify the central angle with the help of the remaining part of circle's angle. If remaining part of circle lies, if the angle on the remaining part of the circle lies in one arc, then the central angle lies in another arc. So, by definition, if an arc subtends two angles, one at center and another on remaining part of the circle, the central angle is always the double of the inscribed angle or the angle that is drawn on the remaining part of the circle. So, by definition and theorem, we write that reflex angle POR is twice angle PQR, which means reflex angle POR is twice PQR is 100, that is 200 degree. Because we need to find the interior angle of triangle PQR, that is OPR, so we need to find angle POR and POR will be 360 minus reflex angle PQR. POR. This is the reflex angle POR and this is the another angle POR. Sum of both these angles, reflexing angle and non-reflexive angle, their sum is equal to 360 degrees. So, when you want to find out angle POR, this is simply 360 degree minus the reflex angle. So, angle POR will be 360 minus 200, that is 160 degrees. Now, in triangle POR, OP is equal to OR because both happen to be the radii of same circle. We can write radii of same circle. then the angles on the opposite sides of these equal sides will be also equal, which is known as isosceles triangle property. That is, OPR will be equal to ORP. Isosceles triangle property. Now, take triangle POR. Angle OPR plus angle ORP plus angle POR is equal to 180 degree. Angle sum property of triangle, which means the sum of three angles of triangle is equal to 180. OPR, because we need to find the measure of OPR, so keep it as it is. And instead of angle ORP, we can write OPR, because already we have proved that angle OPR is equal to angle ORP. So instead of angle ORP, write OPR. And the measurement for angle POR we found was 160 degree. Write 160 instead of angle POR. And all the three angles sum is equal to 180 degree. OPR plus OPR is twice angle OPR equal to 180 minus 160. Twice angle OPR is equal to 20. Angle OPR is 20 by 2. 2, 1, 2 tenths. So the measure of angle OPR is 10 degree. Hope that you understood that question. Now we take another question related to the circles. In this question, we need to find the measurement of angle BDC. Now we see that one of the triangles ABC, the measurement of two angles is given. So by angle sum property, you can find the third angle of that triangle. So if you take triangle ABC, you can find two angles of the triangle are given, and third angle can be found by using angle sum property of the triangle. So instead of angle A, we can write angle BAC, and angle B can be written as ABC, angle C as angle ACB, and sum of all the three angles of triangle is equal to 180 degree. That is angle sum property of the triangle. BAC is unknown, ABC is 69 degree, ACB is 31 degrees, and their sum is 180. Angle BAC, 69 plus 31 is 100 degree, 180. Angle BAC on transposing 100 becomes minus 100, and 180 minus 100 is 80. So the measure of angle BAC is 80 degree. But we need to find the measure of angle BDC. From this figure, you can simply observe that angle BAC and angle BDC both are made on the same segment. Or you can say both are subtended on the same arc. And by definition, by theorem, angles on same segment are always equal in area. Angles in same segment are equal. So we can write angle BAC is equal to angle BDC. As you can see, both angles are spread on the same segment BC, that's BAC and BDC. angles in same side. As angle BAC is 80 and angle BAC is equal to BDC, we conclude that the measure of angle BDC is also 80 degree. And this is the question done. Hope you understand this. Let us take another example, another question from the book. Another interesting question from circles. It says that if non-parallel sides of trapezium are equal, prove that this type of quadrilateral is cyclic. Now we know that a trapezium is a quadrilateral whose one pair of opposite side is parallel. So if we draw trapezium ABCD and we keep side AB parallel to side CD, we can call this quadrilateral as trapezium, where only one pair of opposite side is parallel. And the another thing is given that the non-parallel sides are equal. Now the non-parallel sides are AD and BC, and they are equal. You can keep similar markings on these two sides. So we are given first that ABCD is a trapezium. That means AB is parallel to DC, and another that the non-parallel sides are equal, that is AD is equal to BC. So what do we need to prove? That ABCD is a cyclic quadrilateral. So we know that a quadrilateral is cyclic if its pair of opposite angles sum is equal to 180. So either we can prove that angle A plus angle C is 180, or we can prove angle B plus angle D is 180. This way we can prove that this type of trapezium where non-parallel sides are equal is a cyclic quadrilateral. To prove that, we have to do a construction. You draw a line CE parallel to AD. Parallel to DA. And with that, already AE is parallel to DC, because AE is part of line AB. If AB is parallel to DC, that is given as it is a trapezium, we can write that AE, which is part of AB, is also parallel to DC. Now, if we concentrate on quadrilateral AECD, we find that the opposite sides of that quadrilateral are parallel. Hence, by definition, it forms a parallelogram. So we can say AECD is a parallelogram. So when it is a parallelogram, then its opposite sides are equal. Then AD is equal to EC. Opposite sides of parallelogram are always equal. And already AD is equal to BC. This is given. So by comparing these two equations, comparing first and second, we get that EC is equal to BC. If you take triangle BEC, and already we proved that EC is equal to BC, then their opposite angles are also equal by isosceles triangle property. Isosceles triangle, because the opposite two sides are equal, and when the two sides are equal, then by definition the opposite angles drawn or formed on these two equal sides are also equal. We can say then therefore angle BEC is equal to angle CBE. You can put numerical there, or you can say angle 1 is equal to angle 2. Keep it as equation 3 and write isosceles triangle property. Equal sides of the triangle have equal angles opposite to them. Now, take this as angle 3 and this as angle 4 and this angle as 5. Now, we can write angle 3 plus angle 4 is 180. Now, how is angle 3 plus angle 4 equal to 180? Because if we take AB and CD as two parallel lines intersected by another transversal AD, then the angles formed in the interior of the transversal are 3 and 4 and their sum is equal to 180. We call these co-interior angles. Now, again AD is parallel to EC. Therefore, angle 3 is equal to angle 1. This is corresponding angles. Because AD is parallel to EC and AB forms a transversal, then this angle 3 is equal to this angle 1 because they form corresponding angles. If you compare 3 and 4, now compare 3 and 4, we get angle 2 is equal to angle 3. Keep this as equation 5. Now, again, if you take AB and CD as parallel lines and AD as transversal, you can say that the sum of angle 3 and angle 4 is 180 because these form co-interior angles on same side of the transversal. There we write AB parallel to DC and AD is transversal. Therefore, if AB is parallel to DC and AD is transversal, then angle 3 plus angle 4 is equal to 180. And the reason for that is co-interior angles. Now, instead of angle 3, what can we write? Angle 2. So, or instead of angle 3, write angle 2 plus angle 4 is equal to 180. From the figure, you can see angle 2 is angle B and angle 4 is angle D. And what is their sum? 180 degree. That means in quadrilateral ABCD or trapezium ABCD, we are able to find that the sum of the opposite angles is equal to 180, which means that trapezium ABCD is a cyclic quadrilateral. Hence, it is proved. As sum of the opposite angles is 180, it is proved that ABCD is cyclic quadrilateral. Is cyclic trapezium. So, whenever in a trapezium, if non-parallel sides are equal, then it always forms a cyclic quadrilateral. And to prove cyclic quadrilateral or trapezium, we need to find the sum of the opposite angles equal to 180. And that we did. Hope you understood this question. Very interesting one. We are given two circles intersect at 2 points B and C. We draw the figure. Now, these intersect at 2 points B and C. Through B, two line segments ABD. This is ABD. And another PBQ. PBQ is this one. Another line segment, are drawn to intersect circles at A, D and P and Q respectively. This is A, P, D and Q respectively. Prove that angle ACP is equal to angle QCD. This angle ACP is equal to angle QCD. This angle. We need to find that angle ACP is equal to angle QCD. Now, for angle ACP and angle ABP, we find the relation between the two angles is that angle ACP and angle ABP both are formed on the same segment. So, we can write angle ACP is equal to angle ABP. Angles on same segment. Now, if you observe carefully, these two angles are made on the same arc. We call it same segment. Now, you can see angle ABP is the remaining part of the angle that is lies on the circumference, and ACP also lies on the remaining part of the circle. And both these angles have the same arc AP. You can observe angle ABP and angle ACP are the two angles on the remaining part of the circle, on the circumference of the circle, and both are subtended by the same arc AP. These angles are equal and we call them angles in the or on same segment, or angles in same segment. Now, angle ABP, keep it as equation 1, angle ABP and angle QBD, these are equal. How? Because these form vertically opposite angles, and we know that two angles are vertically opposite angles and they are equal when any two straight lines intersect in a point. When two straight lines intersect in a point, the opposite angles so formed are always equal and are called vertically opposite angles. So, you can write angle ABP is equal to angle QBD. And why are they equal? Because they form vertically opposite angles. Now, compare first and second. You compare first and second. Now, you compare these two equations and you will find out that ABP is the same angle in both the equations. By comparing them, we get angle ACP is equal to angle QBD, and put this relation as equation 3. Now, ACP angle is equal to angle QBD, that angle. Now, observe from this circle, you can find that angle QCD, this is QCD, and this is angle QBD. Both angles are formed on the remaining part of the circle, that is, both the angles are formed on the circumference of the circle. And you can see that RQD subtends both these angles. It's QCD, then it's QBD. QD subtends both these angles on the remaining part of the circle, and hence these angles are equal. We call them angles in same segment. So, now we can write angle QCD is equal to angle QBD. Put as equation 4 and write reasons, angles in same segment. And the same segment is QD. Now you compare equation 3 and equation 4. What do you get? QBD is equal, same in both the equations, and we are able to prove that angle ACP is equal to angle QCD. So, angle ACD is this one angle, ACP is this angle, and QCD is that angle. These two angles are equal. And hope that you understood that question. Now there is another question related to the circles. It says that prove that cyclic parallelogram is a rectangle. Prove that cyclic parallelogram is a rectangle. In this question, we are given two types of correlators. One, that this parallelogram is a this quadrilateral is a parallelogram, and another clue is that this parallelogram is also a cyclic quadrilateral. And we need to find if we have a parallelogram that is also cyclic, then it is a rectangle. So, if you draw the figure like this, suppose this is parallelogram ABCD as given in the question, and also it is cyclic. Then prove that this parallelogram ABCD is a rectangle. Now, by definition, take ABCD as a parallelogram. In a parallelogram, one of its properties is that its opposite angles are equal. Then angle A is equal to angle C. Opposite angles of parallelogram. Keep this result as equation 1. Again, we are given that this parallelogram is cyclic also. Now, it is cyclic. Which means that sum of the opposite angles of cyclic quadrilateral is 180. Keep it as equation 2, and the reason is sum of opposite angles of cyclic quadrilateral is 180 or supplementary. Now, use the result of equation 1 in equation 2. Equation 2. Instead of angle A, we can write angle C and keep angle C as it is, and the sum is 180. Instead of angle A, because angle A is equal to angle C, so you can write instead of angle A, you can place angle C in its place, and angle C plus angle C is twice angle C, which is equal to 180. On transposing, we find angle C is 90 degree. And now by definition, if you are able to prove only one of the angles of a parallelogram is 90, then all its angles are equal to 90 degree, and hence it forms a rectangle. So, hence, in short, we can write ABCD is a rectangle. So, on transposing C, it is angle C is 180 by 2, that is 90, 212 90. So, as we are given that ABCD is a parallelogram, and we are able to find one of its angles is 90. And by definition, if we are able to find in a parallelogram one of its angles is a right angle, then it follows that all the other three angles are also right angles. When all the four angles of the parallelogram are equal to 90 each, it forms a rectangle. We call it a rectangle. Hence, we are able to prove that in a cyclic parallelogram is a rectangle also.